Imagine two particles born from a single event in the vast expanse of the cosmos. These particles, perhaps photons, the fundamental particles of light, are linked in a way that defies our everyday intuition. They are entangled. Imagine them as cosmic dancers, eternally intertwined in a celestial waltz. If one spins clockwise, the other spins counterclockwise, instantaneously reflecting its partner's motion, no matter how far apart they may be. This is the essence of quantum entanglement, a phenomenon that has baffled and intrigued scientists for decades. This interconnectedness, this spooky action at a distance, as Einstein famously called it, is not just a theoretical curiosity. It is a fundamental aspect of the quantum world, a realm where the rules of classical physics break down and the impossible becomes possible. Quantum entanglement opens up a universe of possibilities, from ultra-secure communication to lightning-fast quantum computers. It is a key that unlocks the secrets of the universe at its most fundamental level. In the quantum realm, particles like photons exist in a superposition of states. Imagine a coin spinning in the air, neither heads nor tails, until it lands. Similarly, a photon's polarization, the direction in which its light wave vibrates, remains undefined until measured. Entanglement occurs when two photons are created in a way that links their fates. They become a single quantum system, their properties intrinsically intertwined. Measuring one photon instantly determines the state of the other, even if they are light years apart. If one photon's polarization is measured as vertical, the other instantly collapses to horizontal polarization, and vice versa. This instantaneous correlation, defying the limitations of speed and distance, is what makes entanglement so extraordinary. It challenges our classical understanding of cause and effect, suggesting a deeper connection between particles than previously imagined. The implications of entanglement puzzled physicists for decades. Could this spooky action really be instantaneous, or was there some hidden communication channel between the particles? John Bell, a physicist at CERN, devised a brilliant experiment to test this. Bell's theorem, published in 1964, provided a way to experimentally distinguish between the predictions of classical physics and those of quantum mechanics. Bell's theorem proposed that if the correlations between entangled particles were due to some hidden variables, then these correlations would be limited by a specific inequality. However, if quantum mechanics was correct and entanglement truly involved non-local interactions, then this inequality could be violated. Experiments conducted over the years using entangled photons and other particles have consistently violated Bell's inequality. These results provide overwhelming evidence that the universe is fundamentally non-local. Actions in one part of the universe can instantaneously affect distant parts, a concept that shatters our classical intuitions but opens up extraordinary possibilities for the future of technology and our understanding of the cosmos. The bizarre world of quantum entanglement is not just a theoretical curiosity, it's the driving force behind a new generation of technologies poised to revolutionize our world. Quantum computers, for example, leverage entanglement to perform calculations that are impossible for even the most powerful classical computers. Imagine a computer that could break the encryption codes we use today in seconds, or simulate the behavior of molecules with unprecedented accuracy, leading to the development of life-saving drugs and materials. Quantum cryptography, another exciting application, exploits entanglement to create unbreakable communication channels. Any attempt to eavesdrop on an entangled communication link would instantly alter the entangled particle's state, alerting the legitimate users to the intrusion. This technology could revolutionize secure communications, protecting sensitive data in finance, healthcare, and national security. Section 5. Einstein's reservations, spooky action at a distance. Albert Einstein, despite his pivotal role in developing quantum theory, remained deeply skeptical of some of its implications, particularly entanglement. He famously referred to it as spooky action at a distance, expressing his discomfort with the idea of instantaneous interactions between particles separated by vast distances. Einstein believed that there must be some underlying mechanism, some hidden variables, that could explain the observed correlations without resorting to non-locality. He proposed alternative theories, but these were eventually disproven by experiments. Einstein's skepticism, though ultimately unfounded, highlighted the profound philosophical and scientific challenges posed by quantum entanglement. It forced physicists to confront the limitations of classical intuition and embrace a new understanding of reality, one where the universe is interconnected in ways we are only beginning to comprehend. Section 6. Experimental validation proving Einstein wrong. While Einstein's skepticism persisted, a generation of physicists took up the challenge of experimentally testing the predictions of quantum mechanics, particularly the implications of Bell's theorem. In the 1970s and 80s, groundbreaking experiments, most notably those led by Alan Aspect and his team, provided the first conclusive evidence that Bell's inequality could be violated. These experiments, using entangled photons, demonstrated that the correlations observed between the particles could not be explained by any theory that relied on local realism, the idea that objects have definite properties independent of observation and that interactions are limited by the speed of light. These results, along with numerous subsequent experiments, have firmly established the reality of non-locality and the profound strangeness of the quantum world. Section 7. Quantum communication, instantaneous transmission across the cosmos. Imagine a future where communication is instantaneous regardless of distance. This is the tantalizing promise of quantum communication, a field that leverages entanglement to transmit information in a fundamentally different way than traditional methods. Instead of sending bits of data as electrical or optical signals, quantum communication uses entangled particles as information carriers. Since the state of one entangled particle instantly determines the state of the other, information can be teleported, in a sense, between them. This doesn't mean breaking the speed of light, as no information is actually traveling faster than light. Instead, it's about exploiting the non-local connection between entangled particles to establish a shared reference frame, allowing for instantaneous coordination. Section 8. Quantum medicine revolutionizing healthcare with entanglement. The impact of quantum entanglement extends beyond communication and computation. It holds immense potential in the field of medicine, promising to revolutionize diagnostics, drug discovery, and treatment. Quantum sensors, for example, can be incredibly sensitive, capable of detecting minute changes in biological systems. Imagine diagnosing diseases at their earliest stages with unprecedented accuracy, using sensors that can detect the faintest signals from disease cells. Quantum computers could revolutionize drug discovery by simulating the complex interactions between molecules, leading to the development of personalized medicine tailored to an individual's genetic makeup. Quantum entanglement could also enable the development of new imaging techniques, offering unprecedented views into the human body, allowing doctors to diagnose and treat diseases with greater precision than ever before. Section 9. The future of entanglement, a universe of possibilities. The exploration of quantum entanglement is still in its early stages, akin to glimpsing the tip of an iceberg. We are only beginning to scratch the surface of its potential. As our understanding deepens, we can envision a future where quantum technologies transform our world in unimaginable ways. Imagine teleportation becoming a reality, not in the science fiction sense of beaming matter across space, but in the quantum sense of transferring quantum states, potentially revolutionizing transportation and logistics. Quantum computing could unlock solutions to some of humanity's most pressing challenges, from climate change to disease eradication. Entanglement could be the key to unlocking the mysteries of consciousness, revealing the deep connections between the quantum world and our perception of reality. The possibilities are as vast and mysterious as the universe itself. Section 10. A call to explore unveiling the mysteries of the quantum realm. Quantum entanglement stands as one of the most profound and awe-inspiring discoveries in the history of science. It challenges our classical intuitions, reveals the interconnectedness of the universe at its most fundamental level, and opens up a universe of possibilities for future technologies. As we delve deeper into the quantum realm, we are challenged to expand our understanding of reality, to embrace the strange and counterintuitive. This journey of exploration requires a new way of thinking, a willingness to abandon preconceived notions and embrace the unknown. It is a call to action for scientists, engineers and dreamers alike to push the boundaries of knowledge, to unravel the mysteries of entanglement and to harness its power for the betterment of humanity. The future is uncertain, but one thing is clear: the quantum revolution has begun, and it is driven by the enigmatic dance of entangled particles.